All right, exciting stuff for today. So we are picking up from our last time when we were talking about the fundamental theorem of calculus part 1. Now it's the fundamental theorem of calculus part 2, the sequel. So last time we had the whole idea that if we have some function defined as the integral from a to x of some integrand, some function f of t dt, then the derivative of that function was just that integrand evaluated at x, the upper bound of our integral. So what we saw was the derivative is the inverse of the integral. The derivative cancels essentially the integral. They're opposites. They knock each other out. So let's just take a quick reminder what we have here. So looking at the derivative of the integral of 1 to sine x of the square root of 1 minus t squared dt, I have no idea how to do anything with that integral. But what we have from the fundamental theorem of calculus part 1 is that the derivative of this is equal to that function 1 minus t squared evaluated at our upper bounds. We have 1 minus sine squared x. But I also need to remember that I've got the chain rule. The derivative of sine of x is going to be multiplied by cosine of x. That was d dx of sine x. Gave us that cosine. Now just another little bit of fun thing to do here. We can reduce this, simplifies. I recognize that 1 minus sine squared is actually one of our Pythagorean identities. That's cosine squared times cosine. And since we have the square root of cosine squared, well, that is the square root of a positive, a square number. So this is actually the absolute value. It must always be positive. It's the absolute value of cosine x multiplied by cosine of x. That's our derivative, applying the fundamental theorem of calculus part 1. Big idea, derivative of an integral is the integrand, the function inside, evaluated at that upper bound, that variable. Keeping in mind, we might have to apply the chain rule. The big idea behind this is that the derivative is the inverse of the integral. We're actually going backwards. When functions are inverses, it goes both ways. The derivative of the inverse is the inverse. It cancels the integral. Or the integral is the inverse of the derivative. We've seen that before. Inverse of the derivative, that's when we went through and found antiderivatives. Ooh. So big idea that we have here. What this can say is if we have some function, say f of x dx, then our integral is the antiderivative. Now our antiderivative, we use that big F notation, and we always added a constant. So that's what this is going to give for us. That brings us to the fundamental theorem of calculus part 2, also known as the integral evaluation theorem. So if we have some function that is continuous on a closed interval, where big F is any antiderivative of f, remember our big F, any antiderivative, that's that plus that constant, then we can evaluate an integral when we have that lower and upper bounds. What we're going to say is that the integral from a to b of our function f of x dx is the antiderivative evaluated at the upper bound, subtract the antiderivative evaluated at the lower bound, where big F is our antiderivative, or the derivative of big F is f, our function. So if we know some antiderivative, then we can evaluate by subtracting the values of the antiderivative from the endpoints a to b. So let's check this out. We're going to evaluate the integral, our very first thing that we're going to try out together. So what this says is our function, f of x, is going to be e to the x. Let's think for a moment that any antiderivative, the antiderivative of e to the x is e to the x plus some constant. Oh, before when we were talking about antiderivatives, we had to find the value of that constant. But let's see what happens. Based upon the fundamental theorem of calculus part 2, this is going to be big F of 3 subtract big F of 1. Or in this case, it's going to be e to the 3 plus c, so that constant, subtract e to the 1 plus c. Ooh, look at that. Our constants actually cancel because we're going to have plus c subtract c. We're left with e to the 3 subtract e to the 1. What we have here, we called it, once again, a definite integral. A definite integral is some numerical value. It is a number. It is a value. It is that area under the curve. So what we see is it does not actually matter what our constant is. When we are evaluating a definite integral, we do not need that constant. Later on, we're going to have something called an indefinite integral, where we don't know how it's defined, so we need that constant. Like what we did, are actually exactly the same when we're looking at antiderivatives. Let's try another one. Find the area under the parabola y equals x squared from 0 to 1. Now, area under, that's how we defined the definite integral. So this tells us that we want the area, so the integral from 0 to 1 of our function x squared dx. Now, this we could define as our limiting factor as n approaches infinity. That is the worst infinity I've ever drawn. Infinity of the sum from I equals 1 to n of xi squared delta x. What we were doing before was we had an infinite number of rectangles. There's our base, there's our height. Well, this notation, our definite integral notation, says the same thing. Well, based upon our fundamental theorem of calculus part 2, the antiderivative of x squared, we can do that, is 1/3 x cubed. Now the notation I'll do is, here is our antiderivative. I do not need plus c because I have a definite integral. We have bounds. My notation, I'm going to put a vertical line, lower bound to my upper bound. This is saying that I'm evaluating from 0 to 1. My upper bound, my lower bound. So that's the notation that I will be applying. So this gives us 1/3, 1 cubed, subtract 1/3, 0 cubed. Well, evaluating, that's 0, so we're left with 1/3. The area under that parabola, so thinking about y equals x squared, from 0 to 1, that area is equal to 1/3. We can exactly evaluate the area underneath a curve. We no longer need those rectangles immediately unless we have something that we cannot find the antiderivative for. Let's keep plugging along. Number 3, evaluate the integral from 3 to 6 dx over x. Ooh, I'm just going to rewrite that a little bit. This is the integral of 3 to the 6 of 1 over x. Well, thinking, okay, 1 over x dx. We know that 1 over x is the derivative, of the natural log. So the antiderivative of 1 over x is the natural log. Remember that we need that absolute value because the domain of 1 over x is all real numbers except for 0. So the absolute value gives us the left and the right side of the y-axis on the graph. We're going to be evaluating this from 3 to 6. Now we do see that the absolute value is not essential here because we're using positive numbers, but in other cases we would still need it. So here we've got, this is going to be the natural log of 6, subtract the natural log of 3. Or using my properties of logarithms, that is the natural log of 6 divided by 3, which is the natural log of 2. That's the exact area under the curve. So if we think y equals 1 over x, from 3 to 6, that is the area under that curve. Another one, find the area under the cosine curve. So there's our function, f of x is cosine x. And we're going from 0 to b, and b is just some value in between 0 and pi over 2. Now b is some constant value. So we're going to find the integral from 0 to b cos x dx. Notice my notation. Every time I have my function and I do have dx. That gives us our variable of integration. That matches, in this case, our function. Antiderivative of cosine. So I'm thinking like that hierarchy. Well, sine, the derivative gives us cosine. The derivative of that gives us negative sine. The derivative of that gives us negative cosine. The derivative of that goes back to sine. The antiderivative, we're going the opposite direction. We're saying what function gave us this as a derivative. So we have cosine. The antiderivative is going to be sine of x, and we're going to evaluate from 0 to b. It's our fundamental theorem of calculus, part 2. So sine evaluated at the upper limit, subtract sine evaluated at the lower limit. So we know sine of 0 is 0, so this is just equal to sine of b. The area under the cosine curve from 0 to pi over 2, there's our pi over 2, up until some point b is always just sine of that value. Let's try another one and see some limitations here. So what's the problem? There is a problem. I'm going to go through something, I'm going to make a mistake, but I'm going to assume that I'm doing things correctly. Now the integral -1 to 3 of 1 over x squared dx, for me it helps to rewrite this as -1 to 3 of x to the -2 dx. That way I know that I'm using my power rule. Antiderivative, so I'm going to add 1 to my exponent, that's going to be x to the -1. And I'm thinking about, okay, if I were to take the derivative, -1 multiplied by something needs to give us +1 as a coefficient. So that's got to be negative x to the -1. And we're going to evaluate from -1 to +3. Now just checking my derivative, d dx of negative x to the -1. I'm going to take that exponent, multiply it by negative, so that's going to get us positive, and subtract 1 gives us -2. Okay, that looks good. Evaluating this integral then, we have, well, this is -1 over x, so evaluated from -1 to 3. So we have -1 over 3 subtract -1 over -1. All right, so negative, negative, that makes that positive 1. So we've got negative 1/3, subtract 1, gives us negative 4/3. All right, but where's the problem? Let's think. This is the area under the curve. So 1 over x squared. 1 over x squared, if I think about that graph, it's shoop. And there's a left side, a right side, and we are going from negative 1 to 3. Oh, look at that. Right at 0, we have a vertical asymptote, so like that area is really infinite at that single point. We should have something that's not negative 4/3. And here's the problem, is that our bounds, negative 1 to 3, our function is not continuous over that interval, over that closed interval. So from negative 1 to 3, our function is not continuous because of x equals 0. So this brings us back, if we go right back to the start, our function must be continuous on that closed interval. In this case, we were not. So pulling things together, differentiation and integration are those inverse processes, or inverses. Fundamental theorem of calculus states we've got two parts. When we have some continuous function on that closed interval, then the derivative of the integral is the integrand, the function inside the integral, evaluated at that upper bound. Remember the chain rule. And the second theorem, fundamental theorem of calculus, part 2, is the integral evaluation theorem. If we find the antiderivative evaluated at the upper bound, subtract the antiderivative evaluated at the lower bound. Now, one more thing. If we have some function that we cannot evaluate, we can always define some function as from some a to x of, say, g of t dt. So if we have that f prime of x is equal to g of x, we can work backwards and say that f of x is going to be that integral because it's the antiderivative plus some constant c if we don't have specific values. We'll use that in the next one. Let's take a look at a bigger example. So here we've got an AP problem from the 2018 free response section. So we have some graph of g. The graph of the continuous function g, this is the derivative of the function f. So we're given right at the start that f prime of x is equal to g of x. Or that's telling us that f of x is the antiderivative of, I'm going to say, g of x dx plus some constant c. That's what that first statement comes up. G is the derivative of f, giving us that. Integration is the inverse, so the antiderivative, the integral, would be our function, but there is that plus c. So g is this piecewise linear function, so we've got line, 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 and then we have this parabola from 3 to 6. Let's take a look at this first part. If f of 1 is 3, what is the value of f of negative 5? So we're given that f of 1 is 3. We need to work backwards for f of negative 5. I'm going to take advantage of this statement right here, that f is the antiderivative of g. We don't know any function for g. We can figure something out, but we do know f of x, and I'm going to use different notation, from some value to x of g of t dt plus c. So now I have to find my function in terms of those bounds. I want to take advantage of, if I do the integral from 1 to 1 of g of t dt, I know that is equal to 0 because our bounds are the same. When our upper and lower bounds are the same, well, this would be the antiderivative of g evaluated at 1, subtract the antiderivative of g evaluated at 1, which, okay, that makes sense, that it's 0. Now, we know that f of 1 is equal to 3, so I'm going to set these bounds. This is going to be the integral from 1, I'm setting that as my lower bound, to 1, that's that x, since that's our input, of g of t dt plus c. So by defining my function that way, I don't care what it is, we know this statement is 0, and then c is 3. So we actually now have a function that f of x is equal to the integral from 1 to x g of t dt plus 3. Let's take advantage of that. We want f of negative 5. So f of negative 5 is then equal to the integral from 1 to negative 5 g of t dt plus 3. Or, recognizing that those bounds are reversed, this is 3 subtract from -5, the integral from -5 to 1 of g of t dt. Let's evaluate this integral. That's the area under the curve from -5 to 1 of g of t dt. So I'm going to go back to this. Make note, we want the integral from -5 to 1 of g of t dt. That is going to be this area from -5 up to +1. I'm going to break this into parts so that here we've got a 3 by 3 square, but it's below the axis, so that is actually an area of -9. Next, we have this triangle. It's below the x-axis. That's an area of -3/2. And lastly, this region is above the curve. We've got another triangle. That area is +1 because it's above the curve. So this integral is actually equal to -9 subtract 3 over 2 plus 1, which gets us -19 over 2. So that's -18 over 2 plus minus 3 pi over 2 is -21 plus 2 pi over 2, -19 pi over 2. So f of -5 is equal to 3 subtract -19 over 2. We've got 25 over 2. Ooh, that's kind of fun. Clear that out. Do part B. Part B, we are going to evaluate the integral from 1 to 6 of g of x dx. So if we go back to our graph, take a look at that, we are finding the integral from 1 to 6. A little bit more up there. Now what I see is we've got this linear piece. Ooh, this area is 4. Then we have the area underneath our quadratic, that parabola. So I can look at this, all right, I can separate this. It's going to be the integral from 1 to 3 of g of x dx plus the integral from 3 to 6 of g of x dx. Now that's useful because this is the integral from 1 to 3 of our function is just that height 2 dx. Plus here, we've got the integral 3 to 6 of our parabola is given by that. We've got 2x subtract 4 squared dx. We have, taking the antiderivatives, we have 2x evaluated from 1 to 3, and as we noticed, that gets us 4. We've got 2/3 x subtract 4 cubed. Check that, yep, evaluated from 3 to 6. So this is going to be plus. Now if we take our 6 substituted in, it's 6 minus 4 cubed, that's 2 cubed is 8. 8 times 2/3 is 16/3. Subtract, take 3 and sub it in. We're going to have 3 minus 4 is -1, -1 cubed is -1, -1 times 2/3 is -2/3, subtract -2/3, and that gives us a total of 4 plus 6, giving us an integral value of 10. Let's try the next one. We're looking, letter C, for -5 to 6. So that full graph there, oops, on what open intervals, if any, is the graph both increasing, so f is increasing, that means that f prime is greater than 0, and concave up, so f prime prime is also greater than 0. Now we know that f prime is g, and so f prime prime would be g prime. Let's try that out. Well, f prime g, g is greater than 0 from, okay, from 0 to 4, and then 4 to 6. So g prime is positive, it's negative over there. G prime, when is that greater than 0? If we look, I'm looking just at that interval from 0 to 4, 1 to 6. Well, okay, we're positive there. 0 to 1. From 1 to 3, really, we're 0. And then at 3 to 4, we're negative. And at 4 to 6, back to being positive. So the overlap there is 0 to 1, 4 to 6. So our open interval is 0 to 1, 4 to 6. And a reason, we can state this and show our sine curve. Now the last bit, find the x-coordinate of each point of inflection. All right, each point of inflection, that's when f prime prime is 0 and f prime prime changes signs. I'm going to go back to the graph. F prime prime is going to be the derivative of g, and that is 0 there. 0 all through there, or positive 0, negative. It doesn't change signs at those points. What happens at x equals 4, g prime prime changes from being negative to positive. So last bit we have x equals 4. There's our reason. See you soon.